This is the second video on L'Hopital's rule, and in this video, this is for BC concepts only that use L'Hopital's rule. So the previous video was all things that are in both the AB and the BC curriculums, but this video is strictly the BC curriculum and how we would need to use L'Hopital's rule in those situations. So we're going to start here with example 7, where we're trying to evaluate the limit as x approaches 1 from the right of 1 over the natural log of x minus 1 over x minus 1. Now, just looking at that right off the bat, if you try to substitute 1 into that, you're going to end up with 1 over the natural log of 1 minus 1 over 1 minus 1. Both of these give you 0 in the denominator. So those are situations where it would be indeterminate, and so we would need to apply L'Hopital's rule to it. However, L'Hopital's rule only works when it's a fraction over a fraction. And it doesn't really matter what those functions are as long as it's a function over a function. This right here is 2 fractions that we have going on. So the first thing that we would have to do is we would actually have to combine these into a single fraction by finding common denominators. So the common denominator is going to be the product of those 2 denominators. So natural log of x times x minus 1. So the first fraction would have to be multiplied by x minus 1 over x minus 1. So we would get x minus 1 from that. And then minus the second fraction would get multiplied by natural log of x over natural log of x. So that would become minus natural log of x in the numerator there. So now that we have that guy, even if we were to try to substitute right now, we would still end up with 0 in the denominator. So we do have to apply L'Hopital's rule to it. So then that becomes the limit as x approaches 1 from the right of, so we're going to take the derivative of the numerator. The derivative of x is 1, the derivative of 1 is 0, and then the derivative of natural log of x would be 1 over x. And then down here, the derivative of natural log of x is 1 over x. This would be a product rule problem. So the derivative of the first times the second, plus the derivative of the second, so that's x minus 1, its derivative is 1, but then times the first function there. So at this point, you would then try to substitute, and if I substitute 1 in, I have 1 minus 1 over 1 over 1 over 1 times 1 minus 1 plus natural log of 1. So in the numerator, we get 0, which is not really an issue. The denominator, though, we end up with 0 plus 0. So the denominator is still an issue. So that tells us that here we need to do L'Hopital's rule again. What I would probably do, though, prior to applying L'Hopital's rule to that, though, is try to write it as a single fraction in the numerator and a single fraction in the denominator. So we're going to do some algebra before we actually apply L'Hopital's rule to this. So the numerator, I can think of that 1 as x over x. So I end up with x minus 1 over x as my numerator. And my denominator becomes, this is x minus 1 over x. And then ln of x, if I multiply him to get a common denominator, that becomes x ln of x all over x. Now I have a fraction divided by a fraction. So I'm actually going to do my good old keep change flip. So I have x minus 1 over x times x over x minus 1 plus x natural log of x. So notice your x's cancel. And so now we're looking at the limit as x approaches 1 from the right of x minus 1 over x minus 1 plus x natural log of x. And hopefully you realize you cannot cancel out those x minus 1s. All right, so now I'm going to do my L'Hopital's rule for the second time. So if I take the derivative of that simplified numerator, that's just a 1. And the denominator, derivative of x is 1, derivative of 1 is 0. For x natural log of x, we have to do product rule. So first times derivative of the second plus second times derivative of the first. So that ends up as 1 over 1 plus 1 plus natural log of x. And I'm already happy because I see where this is going. So now if I try to substitute, I have 1 plus natural log of 1 in the denominator. Natural log of 1 goes to 0, and so we get a final answer of 1/2. So that's probably the most complicated L'Hopital's rule problem you're going to see, where you have to do it multiple times, and you have to use a lot of algebra to rewrite and that sort of fun stuff to end yourself up at 1/2. Now, some other forms that are considered indeterminate besides something over 0 or infinity over infinity are 1 to the infinity, 0 to the 0, and infinity to the 0. Those are all considered indeterminate forms, even though you think 1 to the infinity should be 1. It's not really. And anything to the 0 we're kind of trained to believe is 1. But actually those three things are considered indeterminate. So we can try to apply L'Hopital's rule to them, but we still have to adhere to the whole has to be a function over a function. So it needs to be a fraction that we then try and apply L'Hopital's rule to. So an example of this scenario would be this function right here. The limit as x goes to infinity of 1 plus 1 over x to the x. Now if I try to substitute right off the bat, I end up with 1 to the infinity, which is an indeterminate form. So don't just tell me that the answer is 1. So what we do is we assume that the limit actually exists, and we set that limit equal to y. So you're just going to need to go with me on this, okay? Just follow along with what I do. So the reason we're setting it equal to y equals is because of that x right there. So to get rid of the x in the exponent, I'm actually going to do what? Well, to get rid of the exponent, we can take the natural log of both sides. So this would become the natural log of y equals the natural log of the limit as x goes to infinity of 1 plus 1 over x to the x. Now, those exponents can be moved in front as coefficients as long as the natural log is attached to, in this case, the 1 plus 1 over x. Well, there's that whole limit as x goes to infinity in the way. But one of the things we know about limits is that if the limit of 1 plus 1 over x to the x converges to something, then that also means that the limit of the natural log of that would converge, not necessarily to the same thing, but it will converge. So what that means is that those two things can actually be written interchangeably. The order doesn't really matter to them. I can take the limit of the natural log, or I can take the natural log of a limit, either way. So by doing it like that, I can pull the x in front. And then I can't use L'Hopital's rule on this until it is a fraction that I'm looking at. So what I want to do is I want to turn x times natural log of, oh, I don't need that exponent anymore. X times natural log of 1 plus 1 over x into a fraction. So a trick that I could use is, instead of writing that as x, I could write this as natural log of 1 plus 1 over x in the numerator and 1 over x in the denominator, because 1 over 1 over x would get me back to that x that I had right there. But now I have a function over a function, and I can apply L'Hopital's rule to it. So L'Hopital's rule, remember, is to take the derivative of the numerator and the denominator and then evaluate the limit. Now all of that is still equal to the natural log of y. But I'm going to focus on just the limit as x goes to infinity of this stuff right now. So I'm going to work that over here in red with L'Hopital's rule. So I'm going to do the limit as x goes to infinity of, now if I do the derivative of the numerator, the derivative of natural log is 1 over u, so 1 over 1 plus x, times the derivative of 1 over 1 plus x, which is negative 1 over x squared. And then the derivative of 1 over x in the denominator is negative 1 over x squared, like that. So no more natural log. You will also notice that now I have a negative 1 over x squared in both the numerator and the denominator. Those will cancel out. So this is just the limit as x goes to infinity of 1 over 1 plus 1 over x. Well, if I try to substitute infinity into that, I have 1 over 1 plus 1 over infinity. 1 over infinity is 0, and so this ends up equaling 1, which means that if I go back here in blue, the natural log of y is equal to 1, because that's what this limit turned into. Now, y, back at the beginning, follow me on this scavenger hunt, y was equal to the limit that I've been looking for since the beginning of the problem. So if I can figure out what y is equal to down here at the bottom in blue, that's what that limit will also be equal to. So that means I need to get y by itself, which I can get rid of the ln by doing e on both sides. So y ends up equaling e to the first, which means that the limit as x goes to infinity of 1 plus 1 over x to the x is e, or e to the first. That one was a doozy, so I hope you followed me on it. So if you did, then I want you to pause the video and see if you can give number 9 a try, because it works along the same lines. All right, so I have a nice little color-coded path here for how I evaluated this. You actually have to end up using L'Hopital's rule twice, but the process is pretty similar to begin with as example number 8 there. I rewrote it as y equals, inserted the ln, switched the ln and the limit notation, pulled the exponent in front as a coefficient, rewrote it as 1 over x, and then that takes me over to the red stuff. After the first time of doing L'Hopital's rule, I would end up with 0 over 0, so that meant that I had to do it again, which takes me to the green. Now the first step of the green, I actually rewrote cosine over sine from here. Cosine over sine is cotangent, or 1 over tangent. So that's where the tangent in the denominator came from. Then I just did the derivative of negative x squared and of tangent x, and I was able to evaluate them, and I end up with 0, which takes me back to the green stuff on the left. I set natural log of y equal to 0, put an e on both sides, get a value of 1, and so that means that my original limit has a value of 1. So I've told you that one of the reasons that we were learning L'Hopital's rule is so that it could help us with the whole convergence and divergence of sequences that we've been working on. So the next example that we're going to look at actually has to do with that. So here in example 10, we want to show that this sequence does converge. So we need to evaluate its limit as n goes to infinity. So we would do the limit as n goes to infinity of n squared over 2 to the n minus 1. All right, so obviously if I was to substitute infinity right off the bat here, I would end up with infinity over infinity. So I can apply L'Hopital's rule to this, and that would get me to the limit as n goes to infinity of 2n over, and then 2 to the n is an a to the u, so it's 2 to the n natural log of 2. And then when you do that, that is going to give you infinity over infinity again, so you have to do L'Hopital's rule a second time. You get the limit as n goes to infinity of 2 over 2 to the n times natural log of 2 times the natural log of 2 that was already there, which is irrelevant because it all ends up being 2 over infinity, which is 0, which would tell us that a sub n converges to 0. And that wraps up L'Hopital's rule.